All right, let's go. Let's do them in order though. We'll get to number 3. Number 1 was what? 350 feet?
Yeah.
Sunfish, do they like depth? Holy crap. I'm thinking Sunfish Pond is like a backyard pond. And then it said 350 feet. I don't know what a sunfish is. I have no idea.
God rejected sunfish.
Oh,
Like what's it called?
what?
But listen, they have no defensive qualities. Like they can.
How do you know about sunfish?
I got informed.
From this problem?
Yeah, I was on a call while doing this problem, and my friend was just telling me how stupid sunfish are. They're massive. They don't have anything to defend themselves. They
Really?
don't really swim. They just float at a sea level. Like they're
Must be deep.
yes, very. But what's it called?
Wow, I'm gonna have to Google a sunfish.
Like what's it called? They're
Yeah, really
predators. They just come up to them, take a bite of them, and then leave. What is the sunfish gonna do? Nothing.
All right, so remember, water pressure is the specific weight times Z. They call it Z, right? This is Z, the depth that you're working with. So what's the specific weight of water?
62.47.
62.47. We're gonna get that one, remember. Pounds per cubic foot. Important to remember the unit of that. Yep, and then our Z, 350 feet, that's easy. What'd you get?
64.
20.
2-1.
See, we gotta talk numbers.
2-1-8.
Cause I can't process the 1,000 thing. I got a bad pen today.
864.
21864.50
0.5
unit
pounds per foot.
PSF. 2-1, that's a 2-1. Piece of cake, whole bunch of pressure though. 350 feet, that's really deep. All right, what was the next one we did? 2? 2 was a shallow and a deep.
Yes. 4 feet, 12 feet.
4 feet. And 12 feet. And what you had to do?
I had to calculate the pressure at both ends.
Too easy. Too easy, too easy. Any questions on it? Okay, good. What's the next one? That's the one. So. Reservoir. So some kind of reservoir. Usually they have some kind of, slope to them. Here's this. Top elevation is 82.5. Is that right? Yeah. And then they have a pipe that's a certain length.
50 feet in length.
50 feet in length. This can be drawn a number of different ways. And then what's the elevation of the pipe?
38.0.
38.0 feet. And then down here is sea level. Because that's what we take elevations from, is sea level, right? Our elevation right here is like 300, 400 feet, sea level, right? So if we had a pond here, which we do, the pond at the college elevation would be 300 feet. Everyone kind of get that now? I should have had this conversation because every time I see this, I'm like, what?
So it's between like depth and elevation.
Yeah. Yeah. These are elevations, not depths. Civil engineers, water people talk in elevations. And a lot of the problems kind of in the future, we'll talk elevations. They'll say, this elevation, it would have helped if did they say elevation?
They did say it.
They did. Okay, good. Yeah. So it's just kind of a different way to think about how to come up with depth. In this case, and this pipe could be, you could have drawn it like this. And put the 38 right here, like this. I think I even thought about it like this one time. for some reason. Doesn't matter, you're gonna go with the number anyway, right? So it really doesn't matter how you drew it. If you labeled all of these 38, that's what's important. And it ends up to be that the Z dimension ends up to be the difference between the top of the water and where this cap is. Doesn't really matter what the pipe does, right? Because they want to know pressure. Is that true?
Yeah.
Yeah. So pressure is, again, it's just gamma. Is that gamma? I think is that alpha? I don't know what it is. This Greek symbol, specific weight, times Z, right? So all you have to do is find out that. It doesn't matter that the water travels. The pipe could even look like this. Water pressure is super unique in that it just matters about the top and the bottom, that Z distance, right? So when we put water line in the ground to deliver water pressure to all these homes, I don't know if you've ever seen it, it's a big black plastic pipe, it's huge. But when you see 200 feet of it sitting out alongside the road, it looks like a snake because it's pretty flexible when it's that long. And then they drop it in the ditch and the ditch goes like this a little bit, right? But when the water gets to homes, it's all the same pressure, close. The poor home at the end of the housing development has some less pressure than the first home because we're gonna lose some pressure in a piping system. Not much, maybe 60 compared to 55. And most homeowners are not gonna notice the difference between, their garden hose squirting 20 feet or their garden hose squirting 19 feet. They don't care, or the shower, it's gonna feel the same. All right, so what did we get? We should have got specific weight times Z, the difference, what's the difference? 4.5 feet. And this is our good old 62.47. What'd you get?
2779.915.
2779.92.
Yeah.
Yeah. PSF. Good. Good. We learned that civil engineers talk in elevations. That's what we learned today so far. We're gonna learn some other stuff too. And then you had one more thing to do. What was that? The lab. The lab, what'd you do with the lab? You tried to verify that water does have, how close do we get? 65.4?
I got within 3 pounds.
You got which way, up or down? Up, so you got like
65.63.
It's not bad. Anybody get closer than 3 pounds? 2 pounds? Specific weight of water. What'd you get?
52.4.
It is, but what'd you get from your experiment? Did you get right on 62.4?
Or 62.464.
Woo! Right on the money. Pretty close. Did you play with your numbers until you got it really close? Oh, that's probably what I would have done. Reverse engineer it a little bit.
Yeah.
All right. Excellent. You can keep all those together and turn them in. Pass them this way. And I'll grab them. I'm returning homework while you're passing them that way. For those of you that refuse to pick up your homework, I can deliver it. Oh, then I tried to return that to you. Did I grade it yet? You gotta remind me, you turn it in a bucket, but I'll forget to grade it. I mean, it's not gonna hurt you because it's not zero.
Might be maybe the lab. I forgot to bring it in first.
The specific weight?
Yeah.
Yeah, of course you can.
Thank you.
Before you can.
That's for me. Now I feel really special.
Now we know who's not here.
I feel like you have to do the implication of what I was saying, just a thought though.
Another lab today, so that's fun. We're getting into one of my favorite topics. Not yet, though. We have to do a little more with pressure. Oh, hey. Four? Oh, I was supposed to walk by and get him, wasn't I? Yeah, I think so. Maybe. Sorry about that. What else are you people doing?
I never read it. I got it. It just slapped that silver on. I am like, okay. Thanks.
That's what happened with my own.
Like you bought it.
There was two figures on it, so I was like, this is a very used. Like, oh, well, like somebody was had that.
I mean, they're so they're transparent. So this doesn't happen. Right. Like,
Were you in from that?
oh, yeah.
Homework?
Yeah.
Homework and lab.
Perfect. I just threw them in my book already.
Like,
If I put them in my book, I'll remember to take them.
yeah.
My book's coming apart. More?
Yeah.
Yeah.
Hey, why?
Looks good, Aiden.
Like anything other than.
Nice homework format. Nice drawing of your pond.
The lag.
Yeah, perfect.
And if I have a.
Nice job, Euro.
Thanks.
Looks like an engineer did this work.
You're just a hidden.
Look at that. It's really good. Gonna show off. Look at that. Look at that. Straight edge.
Sorry I'm late, but there was a sinkhole that made my bus and unavailable entirely.
Sinkhole.
Yeah, blocked all the way from like 57 to 8 something.
Did you take pictures?
No, I wasn't there because it's a distance, but
In the road? Sinkhole.
yeah.
Love that. That's crazy. Do you know how much
Yeah, so I had
water?
to take the bus, I'm gonna do the max, the 180 and start, on 180 Burnside.
Yeah.
All the way to the last stop, then get on the 20 from there. That's why I wasn't blocked.
Yeah,
This picture never happened.
I don't know.
yeah, we gotta have pictures,
I don't
Jose.
have to have pictures, I have the actual notification on the app.
Oh, that's cool. There'll be pictures on the news then.
I think on the first page, like, okay, let's just see when my bus is coming. Turns out, none of the days is it coming.
All right, let's talk about sinkholes.
Hey, you
That's
guys remember?
super fun.
That's not a compliment.
Do you guys remember that one that was right off campus?
Yeah, that was huge.
A minute ago, was it a long time ago?
Not this time. Not this.
Sorry.
You're fine, man. You've had a morning.
Yes.
You didn't, the bus did not go in the sinkhole.
Not that I know because they canceled it, they canceled.
Well,
it
you
the
would
whole
know,
day.
you were on the bus, right?
No, I had to go on the max
Oh,
and then take the bus elsewhere.
Wait, and what confirmed the whole thing?
huh?
What confirmed the sinkhole?
Yeah, so
Yeah.
what's a sinkhole? How's it happen?
Uh,
Anyone have any guesses?
tectonic plates,
There's like.
Well,
What's under us right now? What's under us?
tectonic plates.
Dirt, and then what's under the dirt? Potentially, there's a rock layer, not always though. Maybe some sand. We're near the Columbia River. And then what else is down there? Water, a lot of water. I can say it. Okay. I'm not gonna though, because it's startling for something, I'm sure. There's a lot of water under us, right? And we use a lot of water and we pump that water out of the ground. Gresham's one of the biggest cities in the state as far as water pumping. They have more wells like per populate, huh?
Why is so expensive?
I don't want to talk about that. Right, so they pump the water out of the ground, they're emptying the aquifers, so now we have like kind of open space underneath us. Especially this time of year, the rains haven't started, it'll refill, right? We're Oregon, it's awesome. We get lots of water, so we will refill our aquifers, but they go down. Right now, so I have a well in Prineville, right? I dug it. It's 140 feet deep. Static water level in the winter is 60 feet. So static water level is like, here's the well. Can you see this? Yeah. So when they popped it, I don't know when they popped it, but in the winter, static water level is about here at 60 feet. In the summer, it's about here at 100 feet. So that's the change in the aquifer. The static water level tells you what the aquifer is doing. So we empty it all summer long, and then in the winter with the snows and the rains, it fills back up.
Why are wells so deep here, like in sand?
It's just the location of the aquifer, how deep it is. How deep are they, do you know?
They're like,
Cause I'm 440 outside of Beaver Creek, I'm 440 feet. We had to go way deep to get good water. We hit
Yeah.
water at like 200. It was okay, but the volume wasn't very good, so
How did you dig it?
well driller. Yeah,
Makes sense.
You just run one?
yeah, you hire them, pay a lot of money.
Yeah.
Yeah,
there's a, there was a proper, friend of mine owned a property in Terrebonne.
Yeah.
And, he went in his pump house near his little old top shed
yeah,
cabin type thing.
yeah,
And later they realized, cause they had to dig it again, cause it was like not that great.
Yep.
But they dug like, you could have saved so much money, cause you would have not had to dig like 250 feet more deep if you had like moved it 100 feet that way.
that's crazy. Yeah, so you know what, you know how they determine where they dig? Where they're gonna drill the well?
It's like that little stick.
Yeah, some of them, they do what's called a well witcher. Yeah, and they take these two copper rods, any two copper rods. You all can build this yourself. Go buy it. Thin not real big, like over 1/8 of an inch. It's got to be strong enough to kind of hold it straight out. Go to Home Depot, you can buy this for $10, right? A copper rod about this long. Take one end and bend it in a 90. Yeah, you take the other one, you have to have two of them, bend it in a 90, you hold them in your hands and walk around with them sticking straight out. Right, so you walk around, pretty soon they go like this. Water. That's all I can say. I don't know if it works or not, but the old school well witchers will show up with their copper rods and they'll walk around. And I see the wrist going like this,
Those
but
things.
they're not supposed to go like this, right? They're supposed to just rotate in their hands. I've tried it a few times. I'm like, I can't ever get it to move. Like I'm standing on my well and it doesn't move. So I'm like, yeah, I don't know about this.
I did,
But-
I did have my grandpa's house, we found it was water pipe.
He's got one experience and he says it works.
Wait, is there-
I want a bigger sample. I want a bigger sample size.
This is my favorite.
Wire
statistic
magic.
for Oregon.
I will find out where to build this well.
I wanna see pictures, not text.
So there's no science.
So I think there is some science to it, but I don't understand it. It changes from what I understand, it changes the magnetic
I can't hate on it. I can't hate on it.
field in that region where there's water. Like the magnetic field's a little different. And the copper has to be copper.
Right.
And yeah, it's supposed to work. There's well drillers that swear by it.
Interesting.
Like they'll walk your property and that's what they'll say, water here.
Yeah.
Yeah. Cause it's expensive. Like a typical well's 10 grand. You wanna hit water.
Yeah,
If you don't hit water, it's pretty disappointing, cause
Yeah.
it's another 10 grand to do it.
Absolutely.
Okay.
It's like, let's go.
All right. We're definitely off topic here. It's Jose's fault.
Yes, it is, sir.
Patrick, did you have something?
What?
Did you have more information for us? You had your hand up or something.
No, I was just thinking it would be cool to like do a study on it with like a utility marker.
I agree. Okay, here's an example problem, because we're gonna talk about hydrostatic force some more. So we're gonna talk elevations. This is 200 feet at the surface. At the top of this is 100 feet. And this is not to scale. And then at the bottom of this is 70 feet. So again, elevation coming from sea level, so this is up on a hill above sea level. There's a plate, this is a metal plate right here that is 10 feet deep, so 10 feet in depth away from us. So that gives us the area of the plate. Right? And we want to know what's the hydrostatic force on it. So how did we do that?
The force is gonna be different at the bottom of the plate than the top of the plate, right?
So let's be careful with what you're saying is yes, but with the word you're using is wrong. So force is what? What's our unit? Pounds. Pounds is what we're looking for. So that's the first thing you want to kind of zoom in on, like, oh, they're asking for a hydrostatic force. We got to get to pounds, right? But what you're talking about wasn't force, it was pressure. So that's exactly right, though. We have to know the pressure at the bottom, the pressure at the top. We have to draw the pressure diagram and then concentrate the pressure diagram into hydrostatic force. The single force that's really pushing on this plate. Okay, sometimes we'll want the distribution, the pressure. And we can do calculations with that too. Sometimes we want the hydrostatic force. Okay, so let's go for a hydrostatic force. We have to draw the diagram of the pressure curve to get that. So if I was doing it, I'd pull the plate out. I'd probably leave it two-dimensional, right? So it's some kind of plate, side view of the plate. Down here, we have a pressure. Up here, we have a pressure. So we're gonna have to calculate those. This one is more or less at the top. Less, bigger at the bottom. So I'll make that a little more dramatic. And this would be the pressure curve. Right? So we need this here, maybe P1, here, P2. So let's get those. Why does like the Jeopardy tune always comes into my head when I like put students to work? Isn't that weird?
I'd say yes, but I do the same thing sometimes.
Oh, that's really weird. If you and I are doing the same thing, I'm worried.
Not really, I mean, we're used to the show, so.
That's true.
No, it's weird that Zoomer does it.
Did he pass?
Yeah.
I think he did. Yeah. And now they do like guest hosts, which is pretty fun. So they don't have one consistent host, they have like guest hosts of like super intellectual people. They're really bad at Jeopardy hosting. Which is reading, it's really just reading. You have to be really good at reading.
That's clip from the new Wheel of Fortune.
Okay, do your pressures, don't you get sidetracked.
Sorry.
It's my fault, I do it. Oh, I don't know about this pen. Driving me nuts. That's it.
Water, right?
Yeah, we'll say water, but that's a good question. It's not mercury. Not today. Did I do that right?
Yeah.
Good. What do we get for P1? Even?
Yep.
And P2.
8121.1.
Everyone good with that? The engineering firm can confirm that number. Ooh, it's good. We're making money this morning. Now what do we do?
There a Y next to E? Or is it
It's
the-
my gamma,
Or your gamma?
yeah, or my alpha, whatever that is.
No, I think that's gamma, what you're trying to say.
Okay,
This alpha looks like an A.
alpha's on its side like this. Is that alpha? This is like gamma.
Maybe you could Google search like the
I don't know.
the alphabets.
Yeah, the Greek letters.
So what we do, like the 8100 minus the 6200 to find the height of that, and then do the triangle stuff.
Yeah, so what we need to do is we need to concentrate this, but it's a three-dimensional thing, right? Looks like this, where we have lower pressures here, higher pressures here. So essentially, we have to find the area of the curve or the volume of the curve. Right? This is the
Couldn't you
curve
like,
that's acting on the plate. Yep, go ahead.
you could like create like make a rectangle and say that's the 6,000
Yep,
there,
absolutely.
and then you could find the area of the triangle and then you could extend it.
Yep, 10 feet.
With-
That's exactly right. So this is the way to do it without looking up any extra formulas for trapezoids or whatever, right? Is to break it into shapes. You have a rectangle that all of us can find the volume of. The issue is, where's the hydrostatic force of the rectangle? Well, it's in the direct center of that rectangle, right? The thing is, where's the triangular shape? Yeah, the volume is, it's going to be in a different position. So it's tricky. But let's go down that path because that's an easy way to, well, not an easy way, nothing's easy, but that's a simpler way to do it. So find me the volume. Essentially, you're going to find this area 6,000 times. How big is our plate? 30 feet. Yeah, I don't know where oh, the 10's the other way. 30 feet. Right. So we can get this 6,247 times 30 feet. Right? What's that give us? $487,410. Did I do that right?
187,410.
6,247 enter 30 times. Yeah, I did not do that one. 187,410. And what's that unit?
Pounds per feet cube.
Hmm? Careful. Right? This 6,247 was a pressure. Pounds per foot squared. Right? And then we multiplied by 30 feet. So now we are pounds per foot. It's called a line distribution. Pounds per foot here, but then we got to multiply by what? Come on. We took the pressure times this length, 30 feet, but doesn't it go? Like, doesn't it have, this is the 30, what's this dimension? 10. Yeah, so to get the volume, we have to have this times this times this. Right? This is our cube. This one's a pressure, length, and a length. So we have to multiply our 187,410 pounds per foot times 10 feet. Hydrostatic force is pounds. We had to get rid of this feet. So now what do we have? 1874100 pounds. 1,000,008. Holy crap. We're generating some force down there, aren't we? And that's just the rectangle. Where's this applied? Center, geometric center, right there. The rectangle is right there. That's essentially the total force acting on that plate due to that rectangular distribution. So if I go back to my side view, it's right here in the center. Now we have to do the triangle. Triangular volume. We do it the same way, right? We have to find this area. We have to find this area. So we have to know the pressure from here to here. And then we're going to multiply it by its length of 10 feet. And that'll give us the hydrostatic pressure of the triangle. Then we have to position it in the right spot. So let's see here, where can I work? I'll just work over here. This is the triangle. So I know this value was this lower value at 8121.1, and this value was the 6247 number, right? Those are the two pressures that are here. Agreed? So then the pressure here is the difference between the two. All right, so that value right there is going to be the 8121.1 minus, yep, 6247. 1874.1.
Yeah.
Yeah. So that is 1874.1. PSF. How tall is this? 30 feet.
To get the volume, wouldn't you just find the area? And
Yep.
Extend it.
That's exactly right. Area of the triangle. What is the area of a triangle formula?
1/2 based on height.
Yep. Area of a triangle, 1/2 base times height. And then we're going to multiply it by 10 feet, right? And that'll give us our hydrostatic force. So it's the area, and then we extend it to 10 feet depth. force due to the triangle, I get 281,115. Anyone else get that?
Yes.
Yeah,
And so that's just pounds. And where's that at?
it's like,
Correct. Yeah, 1/3 from the 90-degree. So from right here, this gets concentrated 1/3 the height, or 2/3 from the pointy end. And since we're at 30 feet, that's a pretty easy one to do. This one's at 15, right? And the triangle is at 10. 281,115. Well, we're getting close. We just still don't, we have 2 hydrostatic forces. So if the problem said find 2 hydrostatic forces, that'd be great, but normally it doesn't say that. It usually says find the hydrostatic force. So how do we find the single force? Everyone good? Everyone okay with where I'm at here? Side view. This is the triangle, this is the rectangle. So here's the rectangle. The triangle is a little lower right in here. Is it the difference between the 2 forces is the question?
no,
No, they're both real forces, right? And I have them drawn correctly.
there's a resultant force.
So if we sum the forces in the X, there's a resultant force, yep. These 2 are both doing this, they're water pressure, they're pushing on that gate. They're acting in the same direction, correct? And they are horizontal, because I made the gate vertical. Right? So, the F sub, I think they're using V. They use V, I don't know. I would use H, but anyway. I'm gonna use H for hydrostatic force. Not for horizontal. For hydrostatic force. So the total force is just gonna be the combination of these 2. That's pretty easy. You just add them up. Plus. So we're at 468,525. The harder part of the problem is figuring out where it is.
It's 1.8 million and 200.
Did I do that math wrong?
I got 1.8,
Okay,
187,691.
sorry. I just hit I hit add 2 numbers in my calculator, so
I got
I was testing you.
2.1. I way wrong in there.
2,
Right,
8,
we're combining the 1.8.
215,
Yeah.
2,155. Thank you. 2,155.
215.
I get 225.
Right, well, we're talking about just adding the 2.
We are, sir. All right, what's the number?
This
2,155.
215.
That's so not what I got.
You want me to bring up my calculator?
No, I didn't have my glasses on, so I'm gonna believe the firm. I'm just the supervisor. Everyone okay with where we got this number? Yeah? Any questions on how we got it? All right, how are we gonna place it?
Find the elevation.
That's kind of right. I mean, where do you think it is?
12.5 feet.
This is bigger, this is smaller. It's in here somewhere. If these were the exact same number, I'd say it's right halfway in between. But they're not. This is like a lot more weighted than that.
I like the percentage.
If they're between two,
A percentage works. Can we use our statics any way possible, thinking that this thing might be in equilibrium? In other words, there's something holding this thing in place over here, right?
You could treat it like a beam and do the beam stuff that we.
Yeah, so we could say, oh, the resultant is here. I'll call it R at some Y distance. Right? But everything's gotta be in equilibrium, so we could say, oh, well, let's push the equal opposite resultant away. Should be able to do moments, like just calculate moments. This one's creating a moment about this point. This one's creating a moment about this point. The resultant, the location of the resultant, which we know would create the counter moment, right? Because there must be a resultant on the other side of the plate, keeping this thing in equilibrium, because it's in equilibrium, it's not moving, correct? So we just calculate that other resultant on the other side. We need it on the other side so it has a better direction. So you can just use moments. You can say, oh, I'm gonna sum moments at A, and we all remember this because we were statics geniuses 2 terms ago.
I wasn't.
And if you actually never had statics, then you're in trouble on this one.
Yep.
What was the moment? What was that equation? Force times distance. Yeah. So 281,115. 281,115, that number times its distance, 10 feet. And I'm gonna say it's counterclockwise, right? So that's a positive. And then what's the moment for the 187,411 or 100?
Positive,
It's also positive and times
15.
15 feet. And then we have our resultant that's over here, our F sub V, that's 211. Oh man, 2155, 215 times Y, our unknown. We don't know where it is. Wow, this is cool. This is old school statics back in the day. And this one would be negative, right?
Yeah.
Because we're that way.
This one's negative because it's clockwise rotation about A. So that should give us the location of Y. The location of that final hydrostatic force. Yeah, so we have to solve for this. So that was our algebra. How did we do that?
You put everything on the other side, so.
You want everything positive, so you want the equation to be positive equals positive. So this is positive, this is positive, this is negative. It does what? Moves to the other side, becomes positive. So then we can run these two numbers, add them together, and divide by the 2155, 215. Good luck with that.
I got about 13.1. 14.25.
Man, that's a lot of numbers.
How did you? So I. 28115 times 10. So well, it's just like staying the same.
You know, it's
Well, yeah, you just plus divide out. And then
I get 13.04.
I did something wrong.
I got 13.7.
I have 13.17.
Wow.
Well, everyone got their answers.
Uh-oh, that was me. I kicked it. Can I kick it again?
It's on them.
Heh. That's cool. So 2811115 times 10 and 1874100 times 15. And then 2155215 divide. I'll do it again. I get the same number, 13.04.
I got 14.
Anybody else get 1304? I really like my number.
I got 14.
Grayson doesn't either.
14.34 again.
Yeah,
14.35.
14.34. So let's talk through the numbers. Somebody read me off your numbers.
So the 28115.
Wait. I have 28111.
Yeah, sorry, I said it wrong.
Okay.
Plus the 187.
No. It's times 10, right?
I know,
That's 10 plus.
but both of those turn out, the 187 number turned out to be 10 times to one and the other. So it's 28.
Wait, I just want to talk through the equation you're using.
Yeah, so 2811115 times 10 plus 1874100 times 15. And the 215521 gets moved to the other side.
It's 215.
Yeah,
Okay. You didn't say the 5.
sorry.
Okay.
So it's 2811150 plus 2811150. Add those together, divide by 2155215, and I get 14.35.
And several of you do.
Yeah.
All right. What's the number 14? What?
14.34.
Let me get that number.
What he did was he just took the products and added them together. And then
Yeah.
moved the other one to the other side and then divided that.
Well, with the HP, I can just cruise through it, but it's failing me. Unless I'm putting in a number wrong, that's my guess. Got it. Wow. I don't know what number I was missing, but I missed it twice. Pretty solid. All right, good. Now we know where it's at. Excellent. You have a homework that's like that, but we're not done. We have to play with my absolute favorite topic. Buoyancy. Because you have a buoyancy problem too. And then you have a buoyancy laugh, which I'm gonna run out of time for, which I don't want that to happen. Good. Kind of see how we did it to get hydrostatic force. It becomes complicated. So vertical is more complicated than horizontal. Right? If our plate was down here. So we did this one, but if our plate was here. Yeah, so it's just gonna turn into this rectangle, super easy, acting straight down, right? But what if the plate was here?
More complicated.
Yeah, it's more complicated, but it's really very similar to this one in that you have a pressure here, a smaller pressure here, and you develop the same kind of thing. Right? Very simple.
Still perfect.
Always perpendicular. Water pressure is so cool, no matter what's down there, like when you're underwater, it's perpendicular to all your surfaces all the way around you. That's why it's squeezing you equally. Right? You don't get like squished on one side. Even when you lay on the bottom of a pool, like I've done this. If you haven't, you should. If you lay on the very bottom of the pool flat, you would think there wouldn't be any pressure like under you because you're laying on the bottom flat. Well, you can't really get there. You can't get your non-flat body flat to the bottom.
So even underneath you.
Even underneath you, it's pushing up. Yep. That's buoyancy. Good lead in. That was perfect. All right, so when we have an object that is underwater, we now know that this object, I'm gonna make it 6 inches by 4 inches by 4 inches.
It was,
It'll clean up. It's just your eyes, Jose.
my eyes,
Okay. Right, and I'm gonna say this thing weighs 30 pounds. Now, we know what's happening to this top surface. And it's gonna be nice and horizontal. We'll say it's 10 feet deep. 10 feet. Here, we'll use 120 inches. Keep our units the same. What's happening to this top surface? It's underwater 10 feet. We just did this. Yeah, there's a pressure curve pushing down, correct? And we could calculate that pretty quickly. Right, we just have to figure out what the pressure is. Let's do PSI. Pounds per square inch. Still water, yep. No mercury yet. 120 feet deep. No, 120 inches deep, sorry. My two's terrible. Sure miss my good pencil. It has a good eraser. I'll call it P1. It's better. So. But we were gonna stay with PSI, weren't we? Won't do that. We'll have to convert the other one.
Just divide by 0.4.
Yep. What do we get?
52.05833.
Anybody else get that?
What do you say? 52.05833.
I do not. 52.06.
Anyone get that?
Right.
In the unit?
Pounds per square, PSI.
We agree with this?
Wouldn't it be pounds per inch?
Yeah, it's pounds per inch. Because we haven't got to the. So the number that you should get used to. If you want it in PSI, it's 43.49489, right? So. The specific weight of water. In pounds per inch squared is just this number divided by this, which I did wrong, 62.47, enter, 144 divide, yeah, 0.43. Sometimes that gets used, if you're gonna use PSI. Right, and then you take that times the 120, 50.05833. 50.06. Right?
Got 52.
52, agreed. I just said the wrong number. Now what? Yeah, so it was this area, wasn't it? So if we know the pressure here, and the curve is like this. We need that volume, agreed? Pressure's here, we need the volume, we need the hydrostatic pressure pushing down on this object.
53.06 multiplied by 6 times 4.
Yep. Exactly. Just like we did before, 4 times. So we're talking 1,249.4. Down, 1,249.4 pounds down. That's the column of water above that plate.
How would we get that number again?
We're calculating the volume of this rectangular shape, volume of this cube. The pressure is that. Agreed? We calculated it by the specific weight times the depth. We calculated the pressure. And we know the surface area is 4 and 6. So to get this volume, it's length times width times height. 4 times 6 times this height. Kevin, got it? Yep, yes.
So for the two surfaces that are also 6 times 6 by 4.
Yeah.
Can we use that number for the lower pressure?
So you're heading in the right direction. This is the water pressure acting down. There's the same shape down here. Is this what you're talking about?
No.
Yeah, well, on the bottom, this same thing is happening, right? Because it happens on every surface. Right? So down here, it's the same shape, but what's different?
I see something that we missed at the start. So the specific weight is supposed to be cubic, right?
Yes,
And we missed that. So
Good
the
catch.
conversion was wrong.
no, the conversion's good.
It should be
Is it the
divided
unit
by
that's wrong?
17.
We're just taking the 2 of them out. Oh, you're right. Yeah, this has got to be 3. Shit.
So we gotta redo it all.
172.8.
Yeah.
It's divided by.
Dang it. Cruising along, thinking about the future is what I was doing. I was stuck there for a second, like, why is that unit not coming out? Right?
Yeah, it was supposed to be.
I was super stuck there for a second. This is all cubed. Sorry.
Does that mean that the answer is wrong? Or just the unit?
That means this is wrong. And that means this is wrong. Our unit was wrong too.
Everything.
Yeah, sorry about that. 6247.
That was a pretty big miss.
Yep, that's
Should've
big.
seen that.
Makes it, I thought the pressures were
Because
kind
like, when
of,
you're
pressures are
doing
kind
it,
of giant, like
when you're
what?
doing it, when you multiply,
Kevin.
you get the volume.
The result. And what's it called? It would it be?
Well, let's get it in steps. We need this.
Well, it would be 144 inches cubed.
Everything's cubed. If the 12 is cubed,
Conversion factor would be 1728
Yeah,
inches
like the
cubed.
number's different.
yeah. Yeah. I have our pressure. Anyone have our pressure? What do we get?
4.34.
Anybody agree? 4.34 pounds per inch squared. Now it works because we have inches to the third and inches, giving us inches squared. Now we take that times 4 and 6. Anybody got a number?
104.16.
104.16, much better. It's not that deep, it's only 10 feet.
I saw it because like when we
Yeah,
multiplied,
I saw it
it
too.
was gonna come out to pound inches.
I was just thinking ahead to this. All right, so we need this same number down here. This is called the buoyancy force. It's the force acting up on the bottom plate. So we need P2 down here. We have to go through our conversion again, but now it's at a depth of 124. And then we need our conversion. This is P2. Pressure should be similar, right? It's only 4 inches of depth.
4.48.
Yep. And then you take that times the 6 and times the 4. Yep. 107. 5872. How much force is coming down due to the water? 104. How much force is going up? 107. So we have a positive buoyant, right? Buoyant force is always going to be bigger than this top hydrostatic force. Right? It's always going to be bigger if there's a depth. So what's the difference? No, what's the difference between these two?
Like 3 pounds.
Like 3 pounds, yep. The thing weighs 30. Now we have this, 30. Equilibrium tells us what? Is it gonna sink or float?
Sink. It's gonna float.
We have a buoyancy force of how much? Like 2 pounds. Correct?
4.42.
How much?
I think 3.4.
3.42.
3.43.
Okay, that's our buoyancy force. The difference between the top and the bottom is gonna be your buoyant force. If the object weighs 30 pounds, the buoyant force is 3.
Gonna sink.
It's gonna sink, not just slowly, it's gonna sink fast.
An anchor.
Buoyancy, that's how we do it, right?
Wait, it's gonna sink?
Yeah, because.
Some of
pressure keeping
the,
it
some
up
of your
is-
forces, you got 104 going down, you got 30 going down. And you got 107 going up.
What does that spell out?
Yeah.
You have about 27 going down.
Yeah.
Because of the 30.
Because the weight of the object matters. If the object weighed 1.4 pounds,
No, it made me such
It
a
would float.
Beyonce.
It would
No,
float.
I don't want
So-
Beyonce.
The way I see it is simply.
What would it be?
so here, wait, one last thing. Why didn't we calculate all these? Don't all these have this side load too?
Those are neutral, but those aren't. going.
Yeah, they're all doing this. They're not doing up and down. They're not helping or hurting the float. Now, if you take the object and you tilt it on its side,
Maybe.
you got a massive problem to
Oh,
figure out whether this thing, because you have to do all the sides then. Right? All right, the good news is there's a slightly easier way to do it that we'll learn next time. And since we're out of time, we'll do the buoyancy lab next time. Unfortunately, Monday, we'll slide it off. You could start on it. What do you think? You could start on and do the calculations, and then we'll do the lab after. Might be a good idea for the weekend.
Does that one have a write-up?
This one will have it right up, but you won't have to do it until after you do the complete the lab. So you don't do it over the weekend. All right, so I'm gonna send you home with it. That means you have to write some numbers down. Your job's gonna determine if this is gonna sink or float.
That was a good load.
No, you're gonna determine if it's gonna sink or float. You're not gonna guess. You're gonna calculate.
Yeah.
So you need to know its size. So go ahead and draw it, and then I'll start giving you numbers. This is the lab. Yeah, and I think I'm gonna scratch your homework for the weekend. This is all you're gonna do.
Cool.
Is try to determine if this is gonna sink or float. Okay. So,
Here. Bird.
they're strange numbers because the laser cut it out.
Do we run to the thousands for units smaller than 2,000?
Don't, yeah, these numbers are good to thousands. So we'll use all this accuracy. Okay, hang on. I'm gonna just give you this overall and let you do the math.
Is that height, both?
Yes. Are you saying, are these the same height?
Yes.
Yeah.
And what about?
Their position doesn't matter, right? Because you're just gonna use its,
Inches.
is inches, yes.
How thick is it?
Yep, we'll get there. We do need it though.
Yeah.
1/8 inch. So this is to the, right, this is to the top. Everyone understand that? Yeah, so you can get the height of those little nubs. Good,
Oh, wait.
excellent.
What fluid are we putting this in?
We're
Just
putting in water.
no mercury?
It is 0.50 ounces.
Mercury.
0.50 ounces.
What? 0.50.
0.50 ounces is what this little scale gives me. How many ounces in a pound?
62.
Yeah.
How much was it again? Other than everything else, though, any kind of weight,
Or it's one definitely second. What?
the weight.
0.50
And that is
ounces.
16 ounces to that.
And what you're trying to determine is if it's gonna float or not. Will it float or not?
What that much is.
Measurements between the.
The position of those little nubs doesn't matter,
0.03.
right? Because you're just calculating a volume.
31.5.
You just need that surface area. So put them wherever you want.
We're gonna take a wild guess, but I think it floats.
Use AutoCAD, use whatever you want to calculate your areas, however you want to do it. What you're trying to determine is if it'll float in water or not. And then we'll float it in water.
Will SolidWorks do this as a simulation?
Yes,
It will do the whole.
it will.
SolidWorks does buoyancy.
You should teach.
You can do buoyancy. Well, it's gonna, you would have to make the final decision.
Right,
What's what?
The depth,
Thickness of it?
what's the depth of like,
yeah, cause the one we did the.
Oh, where is it at?
The one it's sitting at a depth,
That's up to you.
but so the depth changes, does that affect buoyancy?
Good question.
is it?
So,
As
The
it changes,
difference is going to be.
won't the P1 and P2 be,
Okay.
it's up to you.
Doing this, we need to find if it will float, if we just place. it
Yeah.
on the bar.
Yeah. Will it
so is
float?
that a whole separate? Cause like one of those big boats that weigh hundreds of thousands of pounds,
That's lab 2. You're gonna
Set
build,
that in
you're
the-
gonna build a boat.
that's fine.
That's fine.
Or if it's a concrete canoe lab.
Go ahead. Millions of pounds, those things.
Right, so cause I'm thinking like for this last example that we did, if we just set that at the top, we don't have the forces, other than the force of gravity pointing down. But if we were to move it down further, then there would be more force above it that would keep it down.
Yep.
So does the buoyancy change based on?
So buoyancy is significant, specific weight times. C, depth.
Right,
Is that a linear equation or is that a quadratic equation or is that an exponential equation? What kind of equation is that?
it's making my head hurt.
Exactly. Right? It's this. It's pressure equals specific weight.
No, we
times
actually
Z.
do stuff on Thursday, but on.
So depth then,
So since neither one of these have an exponent, this is a linear equation.
Wednesday, we have to do
That means that
Monday.
as you go deeper, for every increase in depth, you have an equivalent increase in pressure. It's equal. It's a
Right.
straight line curve.
it's a proportional.
Yeah.
thing.
It's really.
So if this was squared,
Uh-huh,
then it's like, that's gonna matter
right,
how deep it is.
right,
But since this is like a linear equation, that growth rate, pressure rate is exactly the same for every incremental change.
Not even,
Does
no,
that make
not on
sense?
infrastructure.
That's kind of how you can figure out like,
We're still on,
is the depth getting, is the pressure getting dramatically bigger based on the same amount of depth? No.
Right.
Same amount of depth, same pressure.
Okay.
We're not there yet.
well, basic math would do is like.
Like, our like trick.
Nice job, everybody. I'm gonna pull the homework off. You're just gonna work on this lab.
Sounds good.
Thank you. Right, let's do the usual. Something like send a result, we're gonna get the same answers.
Correct.
I actually want to. We're talking about it, but